Good morning, everyone. So, today our study topic is incoming solar radiation, or in short, it is also known as insolation. Now, the source of energy, most of the energy, apart from the internal energy of Earth, that source is coming from the sun. The sun radiates the solar energy that Earth receives, and all the superficial processes on the Earth are going on. Now, the question comes, where from Sun gets that energy which it releases, and thereby all other planets received that energy. Basically, Sun gets that energy because on the superficial condition as well as the inner portion of the sun, a lot of nuclear reactions taking place, and this nuclear reaction is basically the nuclear fusion process. So in the process of nuclear fusion, basically four hydrogen nuclei having only uh, four protons, these four hydrogen, they fuse with each other and form helium nucleus. Now we all know that helium has two proton in its nucleus and two neutron. So in this process, by nuclear fusion from uh, four hydrogen to uh, one helium, in this process of nuclear fusion, the helium produced by this uh, process have mass about 0.7% less than the summation of mass of these four hydrogen atoms. So by the process of nuclear fusion, when these four hydrogen nuclei fused with each other and produce the helium nuclei, then a mass reduction is observed in this helium. That means this helium is less weight, and that lesser amount is about 0.7% in comparison to the combination of mass of these four hydrogen nuclei. Now, this loss of mass is basically converted to quantum energy, and it is emitted in the form of gamma ray radiation. Now, the excess mass is converted to energy, and if we follow the Einstein equation, that is, energy is a function of mass and c square, that is, c is the speed of light, m is equal to mass and energy. Now if we put the reduce of mass, this amount of mass, in this equation, so m we get, c is the speed of light. Now you can get an idea that the speed of light is enormously high, that is about 3 lakhs kilometer per second. So c square is much higher than that. So increase or change in mass, that will be multiplied with the value of c, then it produce a huge number, and this number is the change in energy. So with very minimum change in mass, that will produce a huge amount of energy. Now, among this huge amount of energy produced by the nuclear fusion process, some energy is used to bind the uh, helium nucleus together, and the rest of the energy is basically radiated from the sun surface, and that radiated energy is taken by all the planets or other celestial bodies as solar energy. Now, this radiated energy is radiated in the form of some electromagnetic waves, and that electromagnetic waves or that radiation uh, energy, different uh, energies or different rays. About 43% is visible light, about 49% is infrared, 7% ultraviolet, and less than 1% is X-ray, gamma rays, and radio waves. Now, if we look at the sun's outer surface, what we see, the visible surface of the sun, that is known as the photosphere. Now, in this photosphere, that is the outer surface of the sun, which we are able to see, in this surface, we can see many white and alternate dark spots. That means within this entire uh, white colored sun, we can see some dark spots. These dark spots are basically the cooler areas of the surface of the sun, from where a lot of energy is already emitted, whereas the bright areas, those are the hot spots, those are the hotter areas, relatively hotter areas. Now the dark spots areas, which is basically the cooler areas, those are known as sunspots, whereas the brighter areas, that is those are the hotter areas, those are known as faculae. Now the energy emitted by the sun is in the form of radiation, and that is in the form of some electromagnetic waves. Now, radiation is the energy that can be emitted by all bodies, any body, which have a temperature greater than absolute zero. Absolute zero temperature means 0 degree Kelvin, or it is equals to minus 273 degree centigrade. So any body which have temperature higher than this absolute zero, that can radiate energy from its surface. Now this radiated energy moves in the form of electromagnetic waves having different wavelength and frequency. Now, as hotter bodies, they have much higher temperature compared to the absolute zero, they will emit more energy having shorter wavelengths and higher frequencies in comparison to the cooler bodies. So cooler bodies, they emit radiant energy mostly having higher wavelengths and low frequency. So we can say that wavelength of this radiant energy, that is wavelength of this radiant energy, that is inversely proportional to temperature. So higher the temperature of the body, that will emit lower wavelength radiant energy. Similarly, lower the temperature of the body, lower temperature means that temperature of the body must be above absolute zero, that will emit higher wavelength radiation energy. So now any planet or any celestial body within our solar system that have its surface temperature above 0 degree Kelvin or minus 273 degree centigrade, that will emit some kinds of radiation energy. So if we compare the radiation energy of sun, and as we know the superficial energy of earth is also higher than minus 273 degree centigrade, so obviously earth is also emitting some kinds of radiation energy. Now if we compare the radiation energy of sun and earth, so as sun have higher temperature compared to earth, it will emit mostly the radiation energy having lower wavelength. In contrast, earth, which has lower temperature, that will emit radiation energy having longer wavelength and low frequencies. So mostly earth will emit radiation energy on this side, and sun will emit radiation energy of all sorts of electromagnetic waves, because our sun have both the dark spots, cooler areas, and hotter areas. So the entire electromagnetic spectrum of rays that is emitted by sun. In general, hotter bodies will emit lower wavelength energies, and cooler bodies will emit higher wavelength energies. Now, the range of different wavelengths involved in the transfer of radiation energy is known as the electromagnetic spectrum. And you can see this electromagnetic spectrum having different rays of different wavelength and different frequency. Gamma rays, these have the lowest wavelength and frequency is highest. With increasing wavelength, you can find X-ray, ultraviolet ray, then the visible light, infrared, microwaves, and radio waves. Now, this entire electromagnetic spectrum, this entire radiation energy, uh, different rays, they can be grouped into two groups. In the first group, that we call the short wave radiation, that includes all the waves having wavelengths less than 4 micrometer, have wavelength less than 4 micrometer, and that include the gamma rays, X-rays, ultraviolet rays, even the visible light. On the other part, the second group is the long wave radiation, which have its wavelength greater than 4 micrometer. So 4 micrometer is the demarcating boundary. The uh, wavelength less than 4 micrometer as the short wave radiation, wavelength greater than 4 micrometer are the uh, long wave radiation, and this long wave radiation includes the infrared rays, microwaves, and radio waves. Now, in this way, Earth or any planet of our solar system receives a lot of energy. Now, the energy received by Earth or any other celestial body within our solar system, among the entire amount of energy received, some amount is absorbed in different portions of the earth. The rest of the amount is radiated back into the space. So there will be a difference between the rate of energy received from the solar radiation and the rate of energy emitted or radiated back to the space. This difference is known as climate forcing, and there must be a balance between the rate of energy received by Earth and the rate of energy radiated back to the space. If this balance is disturbed, then either the Earth will becomes more hotter or the earth will becomes more cooler. So there will be always a balance. Now this climate forcing is expressed in watts per square meter, that is symbolized as W per m square. Now if the sun will bright a very low amount, that means earth will absorb, say for example, 1 watt per meter square more radiation energy, and climate would warm until the outgoing radiation energy, that is the radiation energy emitted back by earth to the space in the form of long wave radiation, that will balance the climate forcing. So if earth receives more energy, until or unless earth will not emit back this extra amount of energy to the space, the earth will be heated up. That means the atmosphere of earth will become more warm. Oppositely, if the earth's emission of energy becomes high, that means it will uh, get the same amount of radiation energy from the sun as it receives previously, but somehow the emission of radiation energy from the earth, that means this portion, is increased. So thereby the amount of energy received by sun becomes lower with respect to the amount of the amount of energy received by earth will be lower than the amount of energy emitted by earth. So thereby earth climate, earth atmosphere becomes cool with time. So you can see with slight change of anything, either receiving of radiation energy from sun or emission of long wave radiation from earth's surface, with slight change of any of these two brings change in earth's climate. Now climate response is the change in globally averaged surface temperature that results from this kind of climatic forcing due to radiation imbalance at the earth surface. Now, what are the factors that influence the incoming solar radiation? Because we all know that the superficial condition of the earth uh, is not changing very rapidly. Um, so the emission of energy from the earth's surface will be more or less uh, constant, and in the latter class or in the next class we will came to know how earth radiates energy in the form of long wave radiation. That means what are the sources uh, by which earth releases radiation energy from its surface. Now before that we have to know that what are the factors by which the incoming solar radiation can vary in time. Now, the source of energy injected into our atmosphere is the sun, that is the external source. Now, this energy can be vary because of these five factors. That means these factors can influence the amount of incoming solar radiation on Earth. The first angle is the angle of incidence of sun's rays. It is also known as altitude of the sun. Second is duration of the sun sign. Third is solar output or solar constant. Fourth is distance between earth and sun. And the last one is the transparency of the earth's atmosphere. So now we'll explain or we'll discuss each of these points elaborately. The first point by which the insolation can be varied is the angle of incidence of the sun's rays. The intensity of solar radiation is depending mostly by the angle at which the sun's rays hit the earth's surface. Now, what do you mean by the angle? That means it is the angle between the incoming solar radiation and the earth surface level. Say for example this solar ray. So this solar ray, incoming solar ray coming in this way, and the average surface of the earth in this portion is like this. So this will be the angle of incidence. Now you can clearly see from this picture that the angle of incidence, which is also called the altitude of the sun, this angle of incidence is largely varies with respect to latitude. Higher the latitude, that means uh, lower the sun's altitude, the radiation energy will be dispersed in more areas. How it happens? You can see that when the radiation energy falling on the Earth's surface hit the Earth's surface vertically, that is perpendicularly at 90 degrees, the same energy will cover this much area. Say for example, we are taking a beam of Earth's radiation energy having the same height, width and length, and uh, we are falling the radiation energy over a flat surface in first um, case vertically, and in the second case in an angle about 45 degrees. Now when the energy fall at 90-degree angle over this flat surface, we can see that it will cover a lesser area compared to when the energy falls in this surface at an angle at about 45 degrees. Now with more lower inclination, the aerial coverage over which the ray falls will be increased. So with more close to 0 degree, it will cover a much wider area. That means with higher altitude or with uh, higher values of the inclination, angle of inclination of the energy, the aerial coverage over which this ray falls, that will decrease. So you can see that near the equator, almost throughout the entire year, sunlight falls at an angle about 90 degrees. But as we move more towards the polar side from the equator, that means with increasing latitude, we can see that the angle of incidence is gradually decreasing. Here the angle of incidence is about 90 degree, and as we move to a higher altitude, angle of incidence gradually decreasing. And with decreasing this um, angle of incidence, the aerial coverage of the radiation energy will become higher. Now, if we consider the same amount of energy falling at the equator and at the higher altitude, so the energy falling over the equator will be concentrated to a much lower area, and that particular portion will be affected by this incoming radiation, whereas the same amount of incoming radiation or the same amount of energy, when it is dispersed to a much larger area, it causes the rays to spread out a much larger surface area, and thereby the energy received at each point in this area will be much less compared to energy received at any point near the equatorial region. So in this way, we can see that the angle of incidence of the sun's rays can affect the amount of energy received at each point over the earth surface. The point more close to the equator receives more energy, whereas the point more close to the uh, poles that will receive less amount of energy. So this variation of incoming solar radiation over the earth's surface is related to the angle of incidence of the sun rays over the earth surface. Now this varies due to the curved nature of the earth surface. Because of the curved nature, as earth is a spherical body, the curved nature of this earth's surface, the sun ray which coming in this way, that will fall at different angle in different latitude of the earth. If instead of this curved surface there will be a flat surface, then on all points over this flat surface the amount of receiving solar radiation will be same. So as the earth surface is curved, that is why the angle of incidence of sun's rays varies with latitude, and due to that the variation of incoming solar radiation occurs over the earth surface, and that will affect differently in different latitudinal places of the earth. The second point for which the insolation varies is the duration of sunshine. Now, solar radiation is only available to Earth during the daytimes. So, very obviously, the longer the span of the daytime, the greater the amount of insolation energy received at that point or at that place. So, length of the day, length of the day uh, is directly proportional to the insolation energy received at that point. Now, this length of the day is solely governed by the latitudinal position of the place over the Earth's surface. At the equator, if we look at the length of the daytime and nighttime, we find that the day length at equator is about 12 hours all over the year, because during the rotation of earth on the elliptical orbit around sun, sometimes due to the tilting of earth axis, northern hemisphere comes close to earth and sometimes southern hemisphere come close to uh, sun. But the equator region remains almost in a fixed distance from the sun. Now, as during this orbital motion of uh, earth around sun, and as the earth axis is little bit tilted, so at different position in the orbit of earth, different hemisphere of earth come close to the sun, so thereby that hemisphere receives more energy, and the um, length of the day in that hemisphere will increase. Say for example, at this time when there is summer in northern hemisphere, that means northern hemisphere faces sun, that means northern hemisphere is more close to the sun, whereas southern hemisphere there is winter and that is relatively farther away with respect to northern hemisphere. Now if you look at the length of the day throughout the entire year at different latitudinal condition of earth, we can see that at equator the day length is about 12 hours throughout the entire year. In contrast, in the poles the daytime varies between 0 to 21 hours. When at the pole, that means at 90° north or 90° south, when there is winter, that means say for example for the present time, if you look at the southern pole 90° south, that will not receive any amount of sun ray. If you look at the position of sun, say for example this is sun and this is our earth, this will be our earth's axis. So you can see the northern axis, this is the equator and this is the axis. The northern hemisphere will receive more energy, whereas the southern pole, this point, the south pole, that will not receive any sun ray during this entire time. So the daytime in southern pole during this winter season is 0, whereas the northern pole, that will have much longer daytime. So you can understand that more and more or larger the daytime, the larger amount of insolation energy received by the earth's surface, and that will affect the climatic condition of the earth more and more. Similarly, lower the insolation energy received by any point over the earth's surface, lower will be the uh, climatic effect due to the um, receiving of incoming solar radiation. And you can see from this graph also that throughout the entire year, the average hours of daylight for any particular point, that varies, that increases. Say for example for northern hemisphere, that increases from March to June, then start decreasing at December. When there is winter in northern hemisphere, then it is the lowest, and again after December the duration of daytime starts increasing in the northern hemisphere. Now simultaneously you can see the average surface air temperature curve in the northern hemisphere also try to follows the duration of daytime in the northern hemisphere. You can see the duration of daytime increasing from March. Similarly, the average surface air temperature in the northern hemisphere also starts increasing. The duration of daytime reach its peaks at June, and average surface temperature of Earth in the northern hemisphere also reach its peaks close to June, mostly in the months of July. So there is a little lag of surface air temperature. But interestingly, the surface air temperature curve and the average duration of daylight in any hemisphere of Earth, they are mostly superimposing or very close to each other. They are following the ups and downs each other. You can see, if you thought that Earth axis is vertical, you can see all the points over the Earth's surface will receive same amount of energy throughout the entire year. So there will be, in this, if this will be the Earth's position, then there will be no seasonal variation. And because of the tilting of the Earth's axis, at some portion of the year, northern hemisphere receives more sunlight. So in this time, northern hemisphere, the daytime will increase, and here exists the summer season. Whereas in the southern hemisphere, mostly the southern poles, that will receive less amount of sunlight, that will receive less amount of insolation. So the night time in southern hemisphere increased, and winter season exists in southern hemisphere. Similarly, at this position, you can see the southern hemisphere receives more amount of insolation energy. So here is the summer, and in the northern hemisphere receives less amount of insolation energy. So here occurs the winter. Now, the next point is known as the solar output or solar constant. As we know, the radiation energy that is radiated from the sun, and the average amount of radiation energy in the form of electromagnetic waves, that average amount of energy received at the peripheral part of the Earth's atmosphere in per unit time, in per unit area, is known as solar output or solar constant. So at the outermost boundary of the Earth's atmosphere, the amount of energy, solar energy received by that atmospheric layer in per unit area, in per unit time, that is known as solar output or solar constant. And the value is about 1.94 calorie per minute per centimeter square. Now, the emission of Earth's energy is more or less constant. However, the emission of Earth of solar energy, emission of sun's radiation energy, can vary with time, and that variation occurs in a 11-year cycle. Although the variation of energy is very less, it only varies about 0.2%. So although the solar constant or solar output uh, varies in a 11 years solar cycle, but uh, that amount is very negligible. The next point for which the insolation energy varies is the distance between Earth and Sun. Now, If we look at the orbital path of Earth around Sun, we know that Earth orbits around Sun in an elliptical way. So the distance between Sun and Earth is not constant during its entire journey. There comes certain positions, mostly in the months of uh, July, when Earth is farthest away from Sun, and this position is known as aphelion. The word aphelion come from two Greek words. One is ap means away or far, and helios means sun. So second portion is basically uh, comes from this word helios. Helios means sun, and the first part, that is ap means away or far. So aphelion indicates the farthest position of Earth from Sun. Similarly, there comes certain time during the months of January when Earth is more close to Sun. This position is known as perihelion. Again, the word perihelion came from two Greek words. Peri means near and helios means sun. So perihelion means the position near to the sun. Now you can see that during perihelion, when Earth is more close to sun, automatically it will receive more amount of solar energy because the sun rays have to travel less distance to reach the Earth's surface. In contrast, when the Earth is in aphelion position, the sun rays have to travel a much longer distance. So compared to perihelion, in aphelion, the Earth's surface receives lesser amount of energy. So theoretically, the northern hemisphere winter becomes slightly milder than the southern hemisphere winter. Why? Because if you look at the perihelion position and the position of Earth axis position is like this. Similarly, at aphelion, axis position is like this. So this will be our equator, and this will be our equator. At perihelion condition during the months of January, in the northern hemisphere there is winter. Now, although there is winter, but the perihelion position, this is near to the sun, so more energy received in the northern hemisphere. In contrast, in aphelion, when there is southern hemisphere winter, the southern hemisphere receives much lower energy compared to the winter time in northern hemisphere during perihelion position. Okay, so the amount of receiving energy in these two hemisphere in two different times varies because of the distance between Earth and Sun. So that is why in aphelion condition, the southern hemisphere of Earth becomes far away and receives very low amount of energy. So winter is more strong here. Whereas during perihelion, in northern hemisphere winter, because of the position of the Earth close to Sun, it will receive relatively higher energy compared to the aphelion position, southern hemisphere winter. So winter is relatively mild. Similarly, the southern hemisphere summer is much warmer than those of the northern hemisphere. You can see that during perihelion, the southern hemisphere of Earth receives more and more energy as the southern hemisphere directly faces the sun, and also due to this perihelion position, Earth is more close to the sun. So the summer temperature in southern hemisphere during perihelion position is greater compared to the summer temperature of northern hemisphere during aphelion position. Although northern hemisphere directly faces the sun, but here the distance is relatively high, so less amount of solar energy is received in the northern hemisphere. So because of the distance of the earth and sun varies at different times of the year due to the occurrence at different position into its orbital path, and also because of the tilting of earth's rotational axis, the temperature difference, at least theoretically, the temperature difference between the two hemisphere seasons are observed. But keep in mind, the temperature difference between the seasons or any um, climatic condition or atmospheric temperature of any place of any hemisphere is not only depending on these factors, but there are also some local factors, like in the ocean current, how close it is from the permanent water body, um, the high hill regions, and lot of these local geographic factors are also responsible along with these uh, large scale causes. The last factor for which the insolation varies is the transparency of the atmosphere. Now, once incoming solar radiation enters into the atmosphere, it is subjected to a series of change before reaching the Earth surface. What are the changes? When the sun rays reach the Earth's atmosphere, it will face lot of air molecules along with some dust particles, liquid water, as well as ice crystals. So lots of restrictions are there to fall the sunlight directly on the earth surface. Only a very minute amount of incoming solar radiation can directly penetrate and fall on the earth's surface. The rest of the amount or most of the amount of the incoming solar radiation is affected somehow by these restrictions. This sunlight, this incoming solar radiation, which face these kinds of restrictions, they are either absorbed completely, the energy completely taken by those restricted bodies, or they are scattered, or they are reflected, or they are diffused by the gas molecules or dust particles or clouds. So you can see most of the energy are not able to directly reach the earth's surface. So thereby more and more aerosols, more and more amount of dust particles, clouds in the atmosphere becomes less transparent. and it results in an increase in insolation absorbed or reflected by the atmosphere. So thereby the transparency of atmosphere also affect any sorts of interference between the incoming solar radiation to reach the earth surface. So that's a brief idea about the variation of incoming solar radiation, how the radiation from sun uh, occurs, and how this energy comes to Earth's surface in the form of different waves having different wavelength and different frequency, and how this incoming solar energy depends on different factors that is discussed in this class. So hope you will understand. Thank you.